Well, this video is for Math 95, and this is more about powers and roots. And this is mostly about notation, okay? So let's talk about the notation. We've used the notation for powers and roots like this, okay? And we've seen that, if we have like x cubed equal to 8, we can take a cube root on both sides, and cube root of 8 will be 2, this will be x, and it's like these 3's are canceling each other out, right, to give you x to the first power. Alright, so there's one thing to think about. We'll come back to this in a minute. Another thing to think about, what if we did the square root of x to the 6th power? Now, if we had some time, and we were all in a classroom together, we might take some time to think about what the answer to this might be, okay? Since I'm here by myself right now, I'll work it out and try to explain it, okay? So here's the issue. Let's go back to what does it mean to be a square root, right? In that previous video, I was talking about how the square root of 9 is equal to 3 because 3 times 3 is 9. So let's apply this idea to this. What can you multiply by itself to get x to the 6th power? Don't think about the square root of 6. That's not what we want. We want something that we're going to multiply by itself and get what's inside here, x to the 6th power. That's x to the 3rd, right? Because x to the 3rd times x to the 3rd makes x to the 6th power. That's what we were just doing with the rules of exponents, right? When you multiply these, you add the exponents. So, the square root of x to the 6th is x to the 3rd. Now that leads to this different kind of notation. This idea and this idea both lend themselves to this different notation. Instead of using the root symbol, a lot of times people say, well, that's almost the same as if we had a 1/2 power, right? And so then when you multiply the powers, you get 6 over 2, which is 3. Oh, well, wasn't that the answer to begin with? And that also works for this situation right here, right? If instead of the cube root of x to the 3rd, we think of this as x to the 3rd to the 1/3 power, that still gives us x to the 1st. Okay, so this is a different notation. Neither one is right or wrong. They're both equally valid. Okay, and that's the point of understanding them, is so that when you see either one, you understand what it means. Okay, is that this root right here will be the denominator of a fraction. All right, this square root right here will have a 2 in the denominator. All right, so this assignment is only about notation. We're really not going to be calculating anything. We're not really going to be solving anything. All we're going to do is go back and forth between these two different kinds of notation, just so that we can try to get used to it. Okay, so on the first page of this assignment, we have all of these expressions using fractional exponents. So let's take a look at it. Problem 2 says y to the 1/5 power, and it says write each expression using radical notation. So this is the 5th root of y. There we go. That's it. Problem 4, we've got 8 to the 1/3 power. That's the cube root of 8, and we can go ahead and solve that and call it 2 if we want to. Same thing is true of problem 6. This is, 64 to the 1/6 power. So that's the 6th root of 64, and that ends up being 2. The important thing here is the notation, understanding that this and this are the same thing. All right, problem 10, we have parentheses AB to the 1/4 power. So that means that this is going to be the 4th root of AB. Okay, problem 12, we've got x cubed, y cubed, and and that is also being raised to the 1/4 power, so that's the 4th root of x cubed y cubed. Okay, now, watch what happens here. So I wrote this as the 4th root of x cubed y cubed. Now, if I raise these to the 1/4 power, I'll get x to the 3/4 y to the 3/4. So there's a third different way to write this same expression. You can write it like this, you can write it like this, you can write it like this. Now, when you go from here to here, notice how the 3's are the exponents and the 4's make the root. Okay? And so this notation, I frequently write it like this, P over R, where P is the power, R is the root. So, when we get to problem 14, yeah, B to the 3/2 power. Okay, so the root is 2. You can put the 2 in there or leave it out. It's the same thing. Square root of B to the 3rd. Okay, that power stays with the exponent, with the base there. Okay, what else? Number 16, 4 to the 7/2, so that'll be the square root of 4 to the 7th power. You can also write it like this, square root of 4 raised to the 7th power. And this one here, you could write square root B raised to the 3rd power. They're all the same. Okay, let's see here. Yeah, problem 20, let's take a look here. We've got 125a to the 2/3 power. So there's two different ways, like I was saying, to do this. You can do it like this with the exponent inside, or you can do it like this with the exponent outside. And they're both correct. So here our root is 3, right? That's in the denominator. And then we can write 125a all squared. Or you can write cube root of 125a and then square the whole thing. Those are both correct. Now, number 22 is a little bit tricky here. Notice that the 8 in problem 22 is outside of the parentheses. To the 3/2. So the 8 is not affected by that 3/2 power at all. Okay? It's going to be stuck outside. The 2 indicates that this is a square root of y to the 6th to the 3rd power. So that's 8 square root y to the 18th. You could write it like this if you want. Let's see, square root y to the 6th all to the 3rd power. Notice I did not include the 8 inside those parentheses because it was not inside these parentheses. So that's problem 22. Let's see. Problem 24. Well, this is where it gets a little bit tricky as well. X cubed plus y cubed to the 1/3 power. This is going to be the cube root of x cubed plus y cubed. And that's all you can do with it. You can't simplify that anymore. So let me talk about this in some depth, because this is something that a lot of people misunderstand. And I'm sympathetic because it is kind of confusing. Okay? So, let's look at our hierarchy of computation here, what governs the order of operations, and the relationship between these processes, right? I've talked about how a repeated addition can be conceptualized as multiplication. Repeated multiplication, you can think of that as giving you exponents. And as a result of that, right, if you have 3 times x plus 7, then that's x plus 7 plus x plus 7 plus x plus 7. And that's 3x plus 21. And that allows you to distribute multiplication across addition or subtraction. All right. with the powers, right, if you, let's say you have x squared y to the 4th power. Well, that's x squared y times x squared y times x squared y times x squared y. There's your x to the 8th power, y to the 4th power. And so you can distribute this exponent across the multiplication that's inside there. And you can do the same thing with division, right? If it were x squared over y, it wouldn't be any different. You can still distribute this exponent to both the numerator and the denominator. This is not that situation, right? Here's an exponent, but you're not distributing across multiplication or division. You're just, if you try to distribute this into the parentheses, you're trying to jump a level. You're trying to go from exponents and distribute it across addition. And it doesn't work like that. I'll show you the classic example here. A plus b squared. Algebra students the world over want this to be a squared plus b squared, but it isn't. And let me show you why. A plus b squared means a plus b times a plus b, right? A plus b times itself. Now we distribute a squared plus ab plus ab plus b squared. And there it is. That's what a plus b squared is, not just a squared plus b squared. Okay? And so you can't distribute this exponent across that addition. You actually have to do the multiplication. And I sometimes talk about the importance of this, you know, this concept that allows you to distinguish things that are true from things that are not true. Okay? Sometimes I talk about a con man who might come by and try to buy this from you for a squared plus b squared, right? Well, it's the same thing. So why don't you sell it to me for a squared plus b squared? Well, this is why not. Because he's cheating you out of this 2ab. All right? So that's the importance of this concept. All right? There are con men everywhere. They never go away. You can look at the history of the con game in literature. It's a constant thing when human beings interact with each other. Okay? The more you understand for yourself, the better you are to not be vulnerable to those situations. So, all right. So that's why you can't say that this is going to be x plus y. Okay? You can't distribute the exponent across addition or subtraction. Okay. Well, let's move on to page 2. We're going in the opposite direction now. We've got these expressions that involve roots or radicals, and we want to write them using fractional exponents, right? Where the power is on top and the root is in the denominator. So problem 26, we've got the cube root of 19, okay? That's going to be 19 to the 1/3 power. Problem 28, square root of 6. Pretty straightforward, 6 to the 1/2 power. And you can use your calculator to do this, right? Check it out. You can do square root 6, and you can do 6 to the 1/2 power, and you should get exactly the same answer. So here, let me show you. Let's get this, there it is. Okay, so now we'll do, let's see here, square root 6. 2.449 approximately, and then we do 6 to the 0.5 power, and hit enter on that one, and there it is. It's exactly the same thing. Okay, and every other calculator should be able to do that as well. Okay, so let's look at some more of these. Problem 30. We've got this square root of a to the 5th power. So that's going to be a. The power goes in the numerator. The root, which is 2, goes in the denominator. A to the 5/2 power. If you want to call this a to the 2.5, that's fine. I don't have a big problem with that. The only place where that becomes an issue is right here. If you call this 19 to the 0.3 power, that's wrong. If you call it 19 to the 0.33 power, it's closer, but it's still wrong. If you want to use a decimal here, make sure that it's a repeating decimal. That is correct now. Now I can take off that does not equals to. Put that bar over it. Now they're the same thing. All right. Problem 32. Let's see here. We have the fifth root of 2n to the fourth. Well, you've got some choices here, because notice that n to the fourth has a power, but the 2 doesn't. This 4 only affects the n, it does not affect the 2. So we've got a couple choices. We could go 2n to the fourth to the 1/5 power. You could say 2 to the 1/5 n to the 4/5. That's also correct. I think that's pretty much it for that one. Let's see here. Problem 34. So now we've got this issue of the 10 being outside of that radical symbol. Okay. Let's see here. Fifth root of xy. Okay. So that means the 10 is not going to be affected by whatever exponent we use here. That'll be xy to the 1/5 power, and you can distribute that into the parentheses if you like, right? Because it's multiplication. You can call it, this is correct, they're both the same thing. All right, 36, 7th root of x to the 3rd y squared z squared. So that'll be that whole mess to the 1/7 power, and then we could call that x to the 3/7, y to the 2/7, z to the 2/7. All right, problem 38. Let's see here, what do we start with? The cube root of 7xy, and that's going to get raised to the 4th power. Okay, so remember when we were doing those problems on the first page that this exponent can go inside the root symbol or it can go outside, but that's going to be the power. So this is going to be 7xy, and the whole thing gets raised to the 4/3 power. I would just leave it like that. You can put it into each individual one, 7 to the 4/3, x to the 4/3, y to the 4/3. That's fine. Or you can just leave it the way it is like that. All right, we got one more problem here. Problem 40. Notice you've got that k outside of the root symbol. Let's see, k, and then the 6th root of a to the 5th b, and then all of that is getting raised to the 7th power. Wow, okay. A lot going on here. Well, that k is going to get raised to the 7th power. And then a to the 5th b is going to be raised to the 7/6 power. And then you can put this, you can apply this power inside the parentheses if you want to. You can leave it like this if you want to. Or we can call this a to the 35/6, b to the 7/6. Either one of these is fine. Okay, so like I said, this is just about notation. And this is the idea right here, okay? So if you've got, let's say, for instance, you've got x to the p over r, then that means you're going to have the rth root of x to the p power. This is the fundamental idea for this assignment. Okay, we'll have one more assignment on these ideas, and that'll be it before the midterm, and then after the midterm, we'll pick up with some related ideas again. As always, if you have any questions, please let me know. Thank you.